All right, so thanks, JD, and thanks to the organizers for inviting me, and thanks everyone for coming to listen. So as JD said, I want to talk about something I've been thinking about related to the TMF-based atom spectral sequence. Okay, so I roughly want to sort of give the talk in these three little sections. So first, I want to maybe talk about some motivational background. Why am I thinking about this problem in the first place? And then I want to go into a little bit more about some of the sort of the necessary characters that are involved and give a more precise statement of the problem that I worked on, and then actually maybe talk about the results. Okay, so I should also say that everything I'm going to talk about today is joint with Mark Behrens and Prasit Bhattacharya. So let's get started with background. Okay, so I don't really, I can't give like a full, discussion into like chromatic homotopy theory or whatever. But I do want to talk about the telescope conjecture. So there is a sequence of homology theories called the Johnson-Wilson E theories, which sort of arose from people studying periodicity phenomena in the Adams-Novikov spectral sequence. And they're really important because they detect things like, when does a finite cell complex have a VN self map? And then they also have associated to them Gauss field localizations. And they're important because there's this theorem called chromatic convergence, which tells us that any p-local finite complex can be reconstructed from the Gauss field localizations for each of these Johnson-Wilson E theories. And then furthermore, the LN localizations, so the Gauss field localization with respect to EN, so this guy is this functor LN, and these things are also sort of manifestly going to be consisting of VN periodic homotopy. Okay, but there are in fact two versions of Gauss field localization with respect to these Johnson-Wilson E theories. There's the usual Gauss field localization, which is obtained by declaring all of the EN acyclics to be contractible. So if EN sees a complex or a spectrum as being trivial, then I declare that thing to be contractible. But then there's also this sort of variant called the finite Gauss field localization. And that's constructed in a slightly different way. Instead of killing all of the EN acyclics, I only kill those ones which are finite complexes. And so there are these two different Gauss field type localizations, but there's always a map relating these two things. So there's always a map from the finite localization to the usual localization, and it's a natural in X. And in the case when X is a type N complex, these two Gauss field localizations actually have fairly nice descriptions. In the case of the finite localization, it's just this telescope on X. So if X is a type N complex, so remember that means that when I evaluate EN homology on that thing, so what it means for X to be a type N complex basically means that there's a self map of X, so that when I evaluate it on EN homology, that's just multiplication by some power of Vn. So then I can invert that self map, and that's what this thing on the right hand means. So in the case that X is type N complex, the finite localization is this very nice telescope thing, this very sort of standard kind of thing. And on the other hand, the usual Gauss field localization is just the Kn localization. Okay, so the telescope conjecture is basically just asking whether or not this map is an equivalence. And you can actually just restrict to the case when X is a type N complex. So you can also think of it as just asking whether or not the natural map from the VN telescope on X to the Kn localization of X, whether or not that's an equivalence. There are various reasons to be interested in this conjecture. Part of it is because this guy over here is sort of the more natural object. So if you read the old literature, for example, if you read Adams and then Smith and Toda, they construct things like the alpha and the beta and the gamma families by finding certain, what we now call Smith-Toda complexes, which are certain type and complexes. And they do things like include the bottom cell and then apply some VN self-map and then project to the top cell. And that's how they produce these sort of periodic families and stable homotopy. Okay, so this is, so that, if you think of it that way, you're immediately led to this kind of thing, okay? But on the other hand, so in some sense, this is like the right thing to think about. But on the other hand, the KN localization is nice because we know that there's a lot of really nice looking spectral sequences, which are related to things like formal groups and cohomology of the Morava stabilizer group and stuff like that, which computes the homotopy of this. So it would be really nice if these things were the same. So that way I could use all these different computational techniques to study this and then be able to say something about this. Okay, but unfortunately, so the telescope conjecture has been around for a while, but unfortunately, we don't really know, we haven't been able to resolve it. Many people have thought about it, but so far we haven't really been able to say one way or the other, except for the case when n equals 1, in which case we do know that the telescope conjecture is true. And that was proven by two people. That was proven by Mark Mahowald when the prime was 2, and it was proven by Miller for odd primes. So the point of departure for today's talk is going to be Mahowald's proof. So I don't want to go into all the details of what Mahowald did or didn't do, but basically the way he resolved the conjecture was he studied the atom spectral sequence based on connective real K theory. And he gave a very sophisticated analysis of the E1 and the E2 page of that spectral sequence, and was able to use the fact that KO had this sort of periodicity in it to argue that the image of J is the only source V1 periodic elements. And then we also know that the image of J is basically the K1 local sphere. So that's so the height 1 telescope conjecture at the prime 2 was resolved through looking at an atom spectral sequence based on an interesting cohomology theory, rather than say mod P homology, in which case you get the classical atom spectral sequence, or Brown-Peterson homology, in which case you get the Adams-Novikov spectral sequence. So he studied something very, very different. Okay, so I and a bunch of other people, so I guess Mahowald started working actually on the TMF-based atom spectral sequence back in the day, and then that was sort of taken up again later by Mark Behrens, Kyle Ormsby, Nat Stapleton, and Vesna Stoyanovska on their paper on TMF cooperations, and then Mark Pressett, myself, and then also Agnes Beaudry and Jolie Xu also started thinking about the TMF-based atom spectral sequence. So a lot of people have thought about the TMF-based atom spectral sequence. And it's actually been, it's done some very interesting things, but it's a very, if you read any of these papers, you'll realize it's a very complicated object. But let me at least recall like what that is, in case you don't remember what exactly how to construct the atom spectral sequence. So TMF is a ring spectrum. So in particular, that means it has a unit map. So there's a map from the sphere into TMF. And you can take the co-fiber of that map, that's TMF overline. And then you can basically iteratively smash this thing with, sorry, I should have said TMF bar. So you just keep smashing this thing with TMF bar over and over and over. And if you do that, you get this tower of co-fiber sequences. All right, so this is the one co-fiber sequence, and then you smash with TMF bar and you get this one, and so on and so on. And then you apply homotopy groups to this, and then you get an unrolled exact couple, and therefore you get a spectral sequence. And the spectral sequence looks like this. Okay, so the E1 page is going to be the homotopy groups of TMF smash powers of TMF bar. So this is one of the reasons why you're immediately interested in TMF cooperations, is because that's sort of the first line of the spectral sequence. Unfortunately, TMF smash TMF, the homotopy of that is not flat over the homotopy of TMF. So this does not have a nice description of the E2 page. But nevertheless, we soldier on and we will keep thinking about it. And there's also an algebraic version of the TMF-based atom spectral sequence. And that's sort of the subject of today's talk. So I'm going to, throughout the talk, I'm going to use this notation where I underline a spectrum to denote its homology, just so I can avoid carrying H's all over the place. But remember or recall that the homology, the mod 2 homology of TMF is A mod mod A2 star. And that's the same as this polynomial algebra on these generators. So it's going to be generated by zeta 1 to the 8, zeta 2 to the 4, zeta 3 squared, zeta 4, zeta 5, zeta 6, etc. And these zetas, these are the conjugates of the usual Milnor primitives. So this is a very nice algebra. In order to explain the TMF-based atom spectral sequence, I need to sort of mention that there is this thing called Hobby's stable homotopy category of A-star comodules. So this is not quite the derived category of A-star comodules, because in that category, equivalences are detected by homology. But in this case, in Hobby's stable homotopy category, equivalences are going to be detected by X over the dual Steenrod algebra. So it's a slightly different thing. I think it's a Gauss-field localization, in fact. But anyway, we want to work in this category because we can talk about cofiber sequences and then mimic the construction that we did in topology. So the homology of TMF is still going to be a ring. So there's a map from F2 into that thing, and you can take the cofiber. And then you just, again, you keep tensoring with TMF over bar, under bar, over and over, and you get an exact couple. And so you get this algebraic TMF atom spectral sequence, and it looks like this. Okay, but notice here, it's important that it's X over A2 star. So that's coming from a little change of rings thing. Okay. So they do a lot of work just to try and even compute the case when n equals 1 here, and they don't even give a complete description of that. So this is very hard to compute, this E1 page. Okay, but I do also just want to mention that there is this sort of schematic of spectral sequences. So basically, we've done there's all these spectral sequences involved, and they sort of all fit together like this. On the bottom is this algebraic TMF atom spectral sequence I just talked about, and on the top is the usual is like the topological TMF atom spectral sequence. But you should notice that this here is the E2 page of an atom spectral sequence for this guy. So I can take a level-wise atom spectral sequence, and likewise, because the bottom converges to the E2 page of the sphere, I can also take an atom spectral sequence vertically. So that's actually very interesting because that means you can start trying to transfer like differentials here to differentials over here. And this thing we know, and X over the dual Steenrod algebra, we know a lot about that. And this is something you can even approach with a computer. And so then you can take the answer, try to extract differentials over here, and then put them over here and things like this. Okay. So, but now what I want to do is I actually want to try and simplify for that is actually coming from Moholwald's work. So so there's a similar sort of scenario where you replace TMF with connective real K theory. And in that situation, basically what Moholwald and I guess then also Moholwald-Lellman do is they basically figured out that all the things that show up here and here are going to be are going to be consisting of certain patterns. They're going to be consisting of BO patterns or BSP patterns or Adams covers of BO or BSP patterns. But the thing is, when you say invert V1 in the BO situation, an Adams cover of a BO pattern or an Adams cover of a BSP pattern just becomes a BO pattern that's been shifted around. Okay, so part of what we're trying to solve, what Mark and Prasen and I were trying to understand by B2 localizing is just trying to understand what are the sort of basic patterns that even show up over here. Because if you look at the computations that people have done in the past, it's like not really clear what the patterns that are showing up are. But if you can V2 localize and then understand the patterns, then you might be able to try and sort of work backwards to figure out what kinds of atoms covers you're taking or this or that. So that's sort of one of the motivations behind this work. Okay, all right, so that's basically the problem statement. Anyway, so now I want to talk about some more of the specific characters involved that sort of come up in studying this E1 page. Okay, so, oh, sorry, I switched from a K to a B for some reason. Anyway, so let me remind you what the mod 2 homology of BO is. So that's A mod A1, and it looks very similar to the homology of TMF. It's going to be this polynomial algebra on these zetas. There's an important filtration that sort of that exists on this thing. So there's a excuse me. So you can write down sort of, it's called the Mohoald filtration or the Mohoald weight or whatever. So basically you can write down a weight function which assigns to every monomial a weight, and you declare, so first off you just say the weight of the zeta i's are 2 to the I minus 1, and then when you take a product, the weight of the product is going to be the sum of the weights. So for example, zeta 1 to the 4, well, the weight of zeta 1 is 2 to the 1 minus 1, so that's 2 to the 0, so that's 1. So weight of zeta 1 to the 4 is 4, okay? Anyway, so then you can define these submodules as the F2 linear spans of all of the monomials M whose weight is less than or equal to 4i. And you can check that that's actually a subcomodule. And that thing is called the ith BO Brown-Gittler spectrum. And it's called that because, at least in this case, I mean, it actually is the homology of something called the BO Brown-Gittler spectrum. So sorry, this is the BO Brown-Gittler comodule. And it is in fact the homology of an actual thing called the BO Brown-Gittler spectrum. Now, the reason this is interesting for us is because there's a splitting of the homology of TMF in terms of these BO Brown-Gittler comodules. So the homology of TMF is this infinitely generated thing. So that maybe is not an immediately easy thing to compute, or whose X is easy to compute. So you want to try and break it up into smaller things. And it does turn out that each of the BOIs are going to be finite dimensional. So now you just have to compute, I mean, granted, you have to compute infinitely many things, but they're all finite. So that's nice. And I just realized, so how do you're supposed to be able to draw in here, right? Is that something? I thought you could draw on the screen for everybody.
I'm not sure. Does anyone know how to do that?
I thought you could do that. Is it called whiteboard? Oh, okay. Yeah, because here I was like thinking I could draw, and I'm not doing it on my iPad right now. So shoot.
Oh, Ming Chuan suggests annotate.
Where is that? Is it under tools? Oh, annotate. Okay. Note text. Oh no. Okay. Oops. Okay. You know what? I'm just going to forget it. It's not crazy important, but BO1, I'll just say it in words. It's a 4-cell complex. It has a cell in degree 0, it has a cell in degree 4, a cell in degree 6, and a cell in degree 7. The 6 and 7 cells are connected by a square 1, 6 and 4 are connected by a square 2, and then the 4 and 0 cell are connected by a square 4. Excuse me. Okay. Okay. Now, the other thing that's really interesting about these BO Brown-Gittler comodules is that they are connected to each other. They're related to each other by these two exact sequences. You'll notice that there's this thing I haven't really defined yet. This is sort of the TMF Brown-Gittler comodule, but honestly, it doesn't really matter what it is because these factors here are going to become unimportant in a minute. But the thing to keep in mind here about these exact sequences is that it does tell you that it does give you, in principle at least, some sort of inductive approach computing the X groups of these Brown-Gittler comodules, right? So for example, on the bottom, right, I apply X and I get a long exact sequence. And if I know the X of BOJ and I know the X of BO1, I mean, I have to take a tensor product and, maybe I can figure out what X of this is, and then maybe it's easy to compute this, then I can sort of figure out what X of this is. And in this slightly longer one, you can think of it as like a 3-line spectral sequence or something. But the thing I want to point out is this tensoring with BO1 thing. So the thing is, if you work out the inductive procedure, what's going to happen is that at some point you're going to try and do all these inductive calculations, but you're always going to be bringing yourself back to computing the X groups of tensor powers of BO1. Okay, that's something that's just unavoidable. So it seems that a good place to start, in the very least, is just computing X of the tensor powers of BO1 if you want to actually do some sort of inductive calculation. Now, remember I said I wanted to understand the V2 local story. So we can work in the V2 local category. And in that case, the short exact sequences become a lot easier to deal with. So remember that when you have a short exact sequence, for example, that becomes a cofiber sequence in the derived category or in this like stable homotopy category. And likewise, this like longer exact sequence, you should think of this as like a filtration of BO2J, where like the filtration quotients are like these sorts of things. Anyway, so now in the V2 local case, things become a bit easier because that term that I told you we can ignore is actually just contractible. And the reason for that is because if I take this guy here and I hit it with X over A2, then by a change of rings theorem, that's the same as X over A1 of whatever this is, right? But X over A1, the multiplication by V2 on that guy is 0. So if I'm inverting something which acts by 0 on the X groups of this, the X groups are 0. And then because the X groups are detecting equivalences, that tells us that this thing is contractible in the V2 local category. So, so that actually makes those exact sequences a little bit easier. So the longer exact sequence just becomes a cofiber sequence now, and it looks like this. So this is telling us that the BO2J guy is going to be sort of being made out of the jth guy and the J minus first guy shifted around. And in the odd case, it's actually you just take the jth guy and you just tensor it with BO1. Okay. All right. I hope I'm not going too fast. Okay, so anyway, so now that's all of the characters here. So now what I want to do is I just want to talk about computing the X groups of BO1 to various powers. Okay, so now I'm going to show you a bunch of charts. Let's see. Okay, this is the first one. So this is X over A2 star of BO1. And you're going to see there's a lot of stuff going on here. So there looks like over here, you guys can see the cursor, right?
Yeah.
I'm going to take. Okay, good. So you see that there's like this BO pattern sort of showing up, right? You got your Z2, Z20, Z, 0, 0, 0, Z, et cetera, et cetera. You got a BSP pattern looking thing over here. You got another BO pattern, et cetera, et cetera. You got V2 to the 8 over here. That's something that's coming from the fact that you're working in X over A2 star. So you got all this noise. But the thing that is the feature here that I want to draw your attention to is this sort of like hooked thing, is this hooked thing here, and it's sort of like dual hook, so there's this hook and this other hook over here. Okay. So that's BO1, and it has this like nice little pattern here. This is BO squared. Okay, this is a little more messy, but you can kind of see that there's still some sort of familiar characters hanging around.
Can I ask a quick question about the previous chart, just to understand?
Sure.
So you said that BO1 is a 4-cell complex, right?
Yes.
So why don't I see those cells on the 0 line? Do they?
You see one of them here.
Oh, yeah, only one.
But, yeah, but the other, because the thing is that like you would get this from, say, like a algebraic Atiyah-Hirzebruch spectral sequence. And the other ones, because they're connected to previous ones through a square 1 or square 2 or square 4, they're going to support either D1, D2, or D4 differentials. So those ones go away. Yeah.
I'd like to ask a question. What is that box in dimension 39?
That's the polynomial algebra on H21. So it's just to clean up some. Yeah. So there's like a bunch of H21s going off. And so we didn't want to keep trying that.
Well, wait a minute, but just a minute. H21 is in dimension 9. Now, what is the dimension? What
I think it's coming from this, and it's like, yeah. What is H21 in again? I don't remember.
Well, H21. I mean, sort of classically is degree 10, and its job is to, well, in TMF, its job is to kill H2 cubed. But I think maybe it's not on the bottom cell, right? It's H21 on some other cell.
Exactly. Yeah. Exactly. I'm trying to remember more precisely where it comes from in the
H21 could be the Toda bracket nu eta blank. That operator could be H21.
So that would be a 5-dimensional thing. That's a 5 nu eta.
But this H21 stems out from higher cells. This is in degree. So first one we see it's H21 zeta 2 to the 4 in degree 9. So zeta 2 to the 4 I think is in degree.
Yeah, I said the wrong thing. I was thinking about B2 H21 squared. Proceed is right. H21 is in degree. H21 is in degree 5. Its job is that Toda bracket. It kills eta times nu, and it's that Toda bracket. And then that H21 zeta 2 to the 4th that we see in 9, that's it's on the 4 cell. It's H21 on the 4 cell.
Right. And its square kills nu cube, as you just said then. Yeah.
Right.
So another thing strikes me. You've got these 2 hooks, and you say one is dual to the other. And
I didn't mean that they were dual in any real sense.
I know, but they sort of look dual. I see that. I mean, you rotate one 180 degrees, you get the other one. I understand what you mean, but it seems like if you take the first hook and multiply it by the corresponding element in the second hook, you end up in the bi degree of that box in the 39 stem. Is that right?
I actually don't remember.
Well, look at the.
No. So I think that's a little confusing though, because this is not
I know you don't have a multiplication. I know that, but nevertheless, those bi degrees, the bi degree of matching elements in those 2 hooks, if you add them up, you get in the bi degree of your box in the 39 stem. Yeah, I'm wondering if that means
not the
anything.
Bottom of the tower. The bottom of the tower starts 15 degrees further down with the H21 multiplications. The box is just it's not the bottom part of the tower.
Okay. All right.
Yeah, I haven't considered that before, so I honestly don't know.
All right.
Any other questions?
It's a provocative chart.
Very much so, yeah. They're only going to get more provocative though, so. But okay, so this is BO1. So this already is kind of a mess, but it's manageable. This is BO1 squared. Okay, so here's some stuff going on. There's, again, some BO patterns. There's actually, you kind of see right here, this little one over here, there's like a truncated BSP, or sorry, like some atoms cover of BO kind of thing coming up. There's a BSP, et cetera, et cetera. And then there's this sort of like spike interloped with a hook thing. And again, kind of like a dual-ish looking thing, okay? And that's the other, so that's, I mean, so there's all this stuff here, which is also important, but I just want to draw your attention mostly to this little feature over here, okay? And then, yeah, BO1 cubed. Okay, so now we're at BO1 cubed. Okay, so this is getting kind of messy, right? But you do start to see, if you think back to some of the previous BO1s, you're going to start to see some familiar patterns showing up. You again see there's a hook and a hook and a dual hook and a dual hook. Okay, But that's not accounting. And then if you really wanted to pay, like actually like really do all the bookkeeping and stuff, you would see that there's also the corresponding number of BO and BSP patterns and stuff that are sort of accompanying these hooks and dual hooks. Okay, so you should think of those hooks in some sense as like a signature of like BO1. So it looks like maybe there's like 2 BO1s showing up, but that's not accounting for everything, because there's also just this sort of like lonely spike, right? So what's that all about? But at this point, we don't really see any sort of pattern, right? All we see is that maybe there's something showing up. Okay, so this is not the version of this picture that I wanted. Is it over here somewhere? Oh yeah, this is a better version of that picture. So this is BO1 to the 4. Okay, so now you're gonna, okay, so this is also very complicated. So, okay, so you're gonna see a couple things. So there's this sort of interloped hook thing with spikes and the dual-ish looking thing. But then you're also just gonna see, it's a little, so you see this just single spike here, but you're also seeing that there's another sort of single spike here. And then again, if you do all the bookkeeping, you're going to find that the BO and BSPs showing up are also going to sort of be accounted for. So now, now you might start thinking that maybe there's a pattern. And then we also had charts going up to like BO1 to the 7. And we started to see that like these sort of signatures kind of kept showing up and propagating. And they seem to be following some sort of threefold periodicity. And so we started asking ourselves sort of what's explaining that? What's going on with that? Why is this happening? Is there some sort of pattern that's happening? And if so, what is it exactly? So that's sort of the main results of what we've done. I should say maybe this is the picture. So if you look at BO1, so if you look at BO1 cubed, so if you get rid of the stuff that's sort of associated with these 2 hooks, okay, then all that remains is like this spike thing and its associated BOs and BSPs. And that's what this is. All right, so you see that this is the spike, and then there's like a hook, and then like just a H2 multiplication, and et cetera, et cetera. Okay, so this is sort of the pattern that remains after you get rid of those things which look like BO1s. Okay. So there's maybe a pattern. And how do you explain that? So the thing is that if you looked at those charts I showed you, and if you saw all the charts that we had, you would see that there seems to be, this pattern seems to start arising with BO1 cubed. So we got really fixated on BO1 cubed for a long time. So the thing to note though is that BO1 cubed, it's an A2 star comodule. But it's not just an A2 star comodule, it's actually got an action of sigma 3 coming from permuting the factors, okay? So that actually also makes it a module over this group ring over sigma 3. And that's really useful because that helps you come up with a way of finding a decomposition of this comodule. So one of the ways you can do that is if you find some idempotents inside the group ring, which sum up to 1, then those are going to give you projection operators and give you a decomposition. And these are the idempotents that we found. It's fairly straightforward to see that they sum up to 1, and notice that F1 and F2 are conjugate. So because you have this set of idempotents, you're going to get a decomposition of BO1 cubed. So you're going to get a copy coming from F1 and F2 and from this E thing, okay? So these are going to be some subcomodules. And then because F1 and F2 are conjugate, these 2 factors are actually the same. Okay. So that's really interesting because, you saw these 2 BO1 type patterns showing up. So, and you're seeing 2 of the same thing showing up in this sort of decomposition arising from this group ring. So you might think that actually these 2 things are just going to be equivalent to BO1. And that turns out to be true. They turn out to look like this. They turn out to be a sort of shifted copy of BO1. And the way you can actually do this in a really like sort of hands-on sort of way. BO1 is only like 4 cells. So BO1 cubed is like, 4 cubed, however much that is, and then you like basically start applying F1 to all of to like sort of the obvious basis, and you can start drawing, use the Cartan formula, and you can start drawing the cell diagram that this thing is, and then you start seeing that there's a B01 inside, and that like the co-kernel or something is like an A2 mod A1 tensored up with something, and it's all very actually down to earth to sort of derive this type of equivalence. Okay, but that sort of leaves this guy, this sort of mysterious factor. So then we were like really interested, what is this thing? So that, let me sort of remind you what that thing is. That's this guy. So this is this E star BO1 cubed thing. This is the stuff that remains after you get rid of those BO1 patterns. So we were really sort of interested in so this is a very nice pattern, but the thing was, we wanted to say that we would get some sort of pattern that would describe all of the BO1 to the Ks. So we were really interested in this guy, and we wanted to say things like, if I take this module or co-module and I tensor it with BO1, it's going to be something that we understand, okay? And we were really stuck on this for a really long time. Like, we are just trying to understand what the hell this thing is. But it turns out it's something really interesting. And with that, I want to take a sort of a weird turn, and I want to talk about TMF03. So TMF is a thing which comes from elliptic curves, and elliptic curves have these things called level structures, and those sort of in turn give rise to variations on TMF. And there's one really important one that was studied a lot by Mahowald-Resk first, and then also by Mahowald-Davis. And that's this TMF03. So it's coming from elliptic curves with a gamma 03 level structure. We don't necessarily care so much about all the elliptic curve stuff, but what Mahowald-Resk and Mahowald-Davis found was that you can actually sort of write down TMF03 as TMF smash with a finite cell complex. And in fact, there's like 3 or 4 cell complexes that you can smash TMF with to give you something which is equivalent to TMF03. And I want to sort of remind you of what one of those is. So they show that if I look at nu squared, so I can look at nu squared, and that's the map from S6 into S0. And then I can include S0 as the bottom cell of the 7-fold suspension of the Spanier-Whitehead dual of BO1. They show that this map actually extends to a map from the 6-fold suspension of BO1 into the 7-fold suspension of the Spanier-Whitehead dual. So they take the cofiber of that map, they call it Z. They show that Z has a map into TMF03. And then because TMF03 is a TMF module, you can induce up to a map from TMF smash Z to TMF03. And they show that that map is an equivalence. Okay.
Can I ask a question? So
Sure.
if I have it right, this Z is a complex with 6 cells.
8 cells.
Oh, 8. Sorry, 8. Right. Okay. Do you have a cell diagram for it?
Oh, not on me, no. But I'm sure. So you can definitely. I'm sure that there is one in Davis Mahowald. I think you can find one in Davis Mahowald. So, right. Okay, but I want to show you the Adams chart. The other thing is that they write down the Adams chart using this. Well, yeah, using this, they like Davis Mahowald sort of give the Adams chart for TMF03, and I think I have it somewhere here. I hope I have it. Is this it? Yes. Okay, this is TMF3. And then, oh yeah, okay, good. They're right next to each other. So, okay. So there's this guy we don't know. And then there's this. So you got this and you got this. So notice there's this spike thing, and then there's this hook thing, and then there's this line thing, and then it repeats. And you got this spike thing, this hook thing, and this line, and then it repeats. So once we realized this, it really sort of kind of makes you think that maybe this thing we're thinking about is some sort of algebraic version of TMF03. And that's precisely what we do. So we basically prove an analog of this theorem over here. So here, so there's a map from some sort of suspension of F2 to F2, which coming from H2 squared. So H2 detects nu, so that's why we're thinking about H2 squared. And we show that this map extends to a map like this. So from BO1 into the Spanier-Whitehead dual of BO1. And so then we just sort of define formally this sort of algebraic version of TMF03 as being the V2 local mapping cone of this map. Okay. And you might notice that there's some suspensions, and that's just to make it's just to make the patterns line up in the right way, basically. Okay. So, and then what we are able to prove is that there is an equivalence between this mysterious factor and some sort of suspension of TMF03. And therefore we get this decomposition of the cube on BO1 in terms of two BO1 patterns and this TMF03 pattern. Okay. And now you're kind of like off to the races with this, right? Because there's another thing that we prove, which is that if you take this TMF03 thing and you tensor it with BO1, then that splits as two shifted copies of TMF03. And now you're basically just in a position where you can say exactly what the V2 local X over A2 star groups of all the tensor powers of BO1 are, right? So for example, I have BO1 4. So I take BO1 cubed. I know that that splits as two copies of BO1 and then a TMF03. So when I tensor with BO1 one more time, I have now two copies of BO1 cubed and a TMF03 tensor BO1. And I know that TMF03 tensor BO1 splits as two TMF03s. And if we go back to the chart, notice, oops, that's not the right one. Sorry. Is this, where is it? Okay, here it is. Yeah. So remember, okay, so we saw that there was two BO1 cubes. So that sort of accounts for these two interloped hook things and their duals. And then there's one of these spikes over here and another. So there's actually, so it's maybe easier to see it over here. There's these two, there's a spike over here and a spike over here, even though it's maybe a little hard to see. So, and these are not, these two spikes are not connected by V to the A periodicity, they're too close. So, so these are those two TMF03s that are showing up. Okay. I think I'm basically, I'm out of time, right? I think so. Okay.
I have another question. In this calculation right here, should there be a V2 inverse in front of everything to the right?
Yes, I totally forgot to write that down. So not in front of the TMF03s, because those are the way I've defined it, sort of already a V2 local thing, but yes, definitely in front of the BO1s. Yeah.
Okay.
Okay. Maybe I'll just sort of end by saying that actually even more is true. Something really nice also happens. So remember we had these cofiber sequences. It turns out that the connecting homomorphism for them is trivial. V2 locally, so actually you get a splitting of the even guys. So if I want to understand the V2 local even BO Brown-Gittler comodule, it actually splits into these two like previous ones. So, you know, at this point, you know, now you can just start trying to write down everything. You know, V2 inverse BO2 is going to split like this. BO cubed is going to split like this. BO4 is going to split like this. You know, BO5 is going to split like this. No, I didn't even talk about BO6, but you know, you can imagine, like, you can kind of see how this is going to go. You know, you just kind of keep doing it over and over, and now you're just sort of keeping track of what patterns are where and what are like where is like the starting point, you know, of these patterns and everything. So this is the meta. This is sort of like the main, you know, I mean, obviously what we did is a little bit more precise than this, but I mean, I think this is a good summary of what we did. We show that the E1 page of the, and sorry, it should say V2 local here. The E1 page of the V2 local algebraic TMF-based atom spectral sequence is going to be completely comprised of the following kinds of patterns. A TMF pattern, which is really F2 algebraically, but it's going to have TMF patterns, BO1 patterns, BO1 squared patterns, and this TMF03 pattern. So yeah, so all right, so that's all I wanted to say for today, and thanks for listening.
All right, let's thank Dominic. So I'm going to open up some breakout rooms. We'll have a half-hour break before the next talk, which will be at 11:30, and people can ask Dominic questions in those breakout